Hi, my name is Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know for the Regents about matter and energy. Now, if we're learning about matter and energy, the first thing I have to talk about is matter. Well, what is matter? Matter is anything that takes up space. Your matter, I'm matter, your computer is matter. Is air matter? Well, does air take up space? What do you think? Maybe. Well, if I go like this, I'm going through air, so it's really not taking up space, right? Well, what about this? This balloon now has matter in it. What's taking up the space? The air. So clearly, air does have matter. Matter, again, is anything that takes up space. And matter can be divided into two different places. Matter could be either a pure substance or a mixture. And let's talk about pure substances first. A pure substance is anything that has constant composition and constant properties throughout the sample. What does that mean? You have no idea what that means. I don't know what that means. It doesn't matter. I'm going to explain it to you. Let's say this is water. Let's say this is pure water. It's just H2O, nothing else. When you turn on your sink, you're not getting pure H2O. There's some dissolved minerals and salts in it. But let's say this is pure water. That means everywhere in this whole sample, there's many, many, many molecules of water in here. But everywhere throughout the whole sample, it's H2O. It's a pure substance. It's not like the water down here is different than the water in here and different than the water here. And if I have water in this beaker and you have water in your home, if it's H2O, it's going to be exactly the same. It has constant properties. Why? Because it's H2O. 2 hydrogens and 1 oxygen. It's a pure substance. It's exactly the same throughout. It's always H2O. That's what a pure substance is. But what you really need to know a pure substance is, more than anything else, you need to know that a pure substance can be either an element or a compound. That's what you need to know a pure substance is. So if the Regent says, what's a pure substance? You say, well, it's either an element or a compound. Let's talk about them. An element represents the simplest form of any substance that cannot be broken down by chemical change. An element cannot be broken down because it's the simplest form. How do you know what the elements are? The elements are what's on the periodic table. The periodic table is made up of all the elements. Those represent pure substances because those are elements and they cannot be broken down. And the symbols of those elements you can get from table S, which shows the chemical names and symbols for all of the elements you need to know about. So an element, whenever you see on the Regents, which of the following cannot be broken down by chemical change, you know you're dealing with an element. A compound, on the other hand, is 2 or more different elements. 2 or more different elements that are chemically combined in a fixed ratio. What does that mean, fixed ratio? Well, if I have water, it's H2O. 2 hydrogens, 1 oxygen. That's the ratio of hydrogen to oxygen in water. 2 to 1, that's the ratio for water, 2 to 1. A compound, again, is 2 or more different elements chemically combined. Now, compounds could be broken down. And it's very important that you know that with a chemical change, you can break down a compound, but you can't break down an element. Well, how can you tell the difference between some compounds and elements? Like, let's say cobalt, for example, is CO. But carbon monoxide is also CO. Well, for elements, their symbols, if there's a 2-letter symbol, like cobalt, the first letter is capitalized and the second letter is lowercase. So CO is cobalt because the first letter is capitalized, second's lowercase, so that's cobalt. If there are 2 capital letters, that means it's 2 different elements. CO is carbon and oxygen, carbon monoxide. So that's how you tell the difference between an element and a compound. Very important that you know that. And compounds cannot be broken down by physical change. They can be broken down by chemical, but they can't be broken down by physical. And if you're not sure what a physical or chemical change are, go to the concepts on them and you can learn more. But just know, elements can't be broken down at all by chemical change or any change. Compounds can be broken down by chemical change, but not by physical change. So remember I told you matter could be separated into pure substances, and then they also can be separated into mixtures. A mixture are two or more pure substances. It could be two elements, a compound and an element, two compounds, but it's two or more pure substances that are not chemically combined. They're not chemically combined, so they can be separated by physical means. You could separate a mixture. For example, let's say you had a mixture of hydrogen gas and oxygen gas. Well, that's not water. Water is when hydrogen and oxygen combine to form the chemical change of water. A mixture, when you have hydrogen and oxygen, and you put it together, it's still hydrogen and oxygen. It still retains the properties that it once had. Hydrogen is still hydrogen, oxygen is still oxygen. When you combine to make a compound, the properties change. Again, hydrogen is flammable and explosive, and it can cause a fire. Oxygen is needed for a fire. When you put them together to form the compound water, it puts out fires. So obviously the properties of those substances change. But in a mixture, it's physically combined, so it's not actually together. Therefore, the properties do not change. They retain the same properties. That's the difference in a compound and a mixture. Now, mixtures can either be homogeneous or heterogeneous. If a mixture is homogeneous, that means even though the properties are not exactly, it's not a pure substance, in that if I have a mixture and you have a mixture, it could be a different type of mixture. But a homogeneous mixture, it looks like the properties are the same throughout. So if you put salt in water and you stirred it up, that whole solution would look the same throughout. But if you put oil in water and you mixed it up, the oil would settle at the top and the water would stay throughout the whole thing and at the bottom. Therefore, it is not the same throughout because you could see the difference in the properties. You could see the oil at one point and the water somewhere else. So a homogeneous mixture is when it looks the same throughout, where a heterogeneous mixture looks different throughout. And most mixtures are heterogeneous. Heterogeneous mixtures, a chocolate chip cookie is a heterogeneous mixture. A piece of pizza is a heterogeneous mixture. A homogeneous mixture is also a solution. A solution, and if you're not sure what a solution is, you can go to the concept on solution. But an aqueous solution, even more important, that just means water is involved. So when you mix salt and water and you get a saltwater solution, that's a homogeneous mixture because it looks the same throughout. Very important you know the difference between homogeneous and heterogeneous. But more important, you know the difference between pure substances and mixtures. So elements and compounds and mixtures. You also have to know how to write particle diagrams for all of them. Let's say we had substances. Let's say we had atom X and atom Y as represented in that you could see in the slide screen. Atom X is a circle, atom Y is a filled-in circle. And you wanted to draw particle diagrams for them. Well, let's say particle diagram for element X, okay? Just a regular circle. You would just see the particle diagram, as you could see, just shows element X in that substance. It's only element X. There are a couple of them, but it's still element X. So it's not a mixture, right? Because it's just the element. There's only one pure substance together. So therefore, that represents an element, a particle diagram for an element. Sometimes elements can be bonded together. For example, we talked about the diatomic molecules. And if you don't remember the diatomic molecules, go to the concept on diatomic molecules. But oxygen, for example, is O2. Now, that's oxygen bonded with another oxygen. Atom Y, let's say that that's oxygen. It has a filled-in circle, but when that becomes an element, you wouldn't just see oxygen by itself. You would see two circles touching and connected. That would be the element for oxygen or any diatomic molecule. Now, you may be asking yourselves, well, isn't that a compound? I thought a compound was two elements combined. Well, it is. That's what a compound is, but a compound is actually two different elements. So in this particle diagram for element Y, it's two of the same elements, therefore it's still an element. So you see a particle diagram for element X and a particle diagram for element Y. You also have to know how to do particle diagrams for compounds. And all you're showing is two or more different elements chemically combined. So let's say there was a compound XY. As you can see, there's one atom of X bonded to one element of atom Y. and that's a compound because they're bonded. And you can have different types of compounds. So this is one compound. You could also have a compound where there's 2 atom X's for every 1 atom Y. And that's another compound, another particle diagram for a compound. And the last thing you need to know for particle diagrams is how to represent a mixture. Well, you could have a mixture, and that just means it's 2 pure substances that are not chemically combined. So let's say you had a mixture, a particle diagram for a mixture of 2 elements, element X and Y. It would look like that. Notice, the elements are there. They're still the same as they were. They're just together, but they're not chemically combined. Therefore, it's a mixture. Also, you can have a particle diagram for compounds, 2 or more different compounds, not chemically combined, but just together in the same area. And as you can see, that's what's happening there. And you could also have a particle diagram for a mixture of elements and compounds, and that's there. So you see that for mixtures, they're not chemically combined, they're in the same area, but you have to be able to write particle diagrams for elements, compounds, and mixtures. Okay, that's matter. Now we need to talk about energy. Now, energy is just the ability to do work, but that doesn't really make sense to anyone out of chemistry, right? Energy, you need to understand 2 forms of energy: potential energy and kinetic energy. Potential energy is what it sounds like. It's the potential you have to have energy. You're not using the energy necessarily, but it's just the potential. It's actually stored energy. Whereas kinetic energy is actually energy you're using, or energy in motion, energy that you're actually using. Potential energy is stored energy, or potential. Kinetic energy is the actual energy that you can and are using at the time. Now, you need to know the different forms of the energies. So there's different forms of potential energy. The 2 major forms of potential energy we need to talk about are chemical energy and nuclear energy. Well, nuclear energy is just the energy in the nucleus. It's the stored energy in the nucleus. And that makes sense because it's in the nucleus, so it's nuclear energy. Chemical bond energy, or chemical energy, is the energy stored in chemical bonds. Let's say we take glucose. You can see glucose there. A lot of bonds in glucose. Each bond has its own energy. And you could see, since there are a lot of bonds of glucose, there's a lot of energy in glucose. That's chemical bond energy. It's the energy storing and holding the bonds together. And that's chemical energy. Again, it's stored energy. The other kind of energy, not potential, but kinetic, energy of motion, energy that's happening. Well, thermal or heat energy is a kind of kinetic energy. It's what makes things hot or not hot because it loses heat or thermal energy. But you need to understand that thermal or heat energy is a form of kinetic energy. Electrical energy is why you can plug in a stereo and you can listen to it, or you can turn your lights on, because electrical energy is when the electricity or electrons are causing energy to be formed. And there are other types of energy, like light energy, all types of kinetic energy, energy of motion. You also have to understand energy conversion. Sometimes energy can be converted from one form to another. You can't gain or lose energy, but you can convert it from one form to another. Now, there's a great demo you can click on, gummy bear demonstration, where you could see in gummy bear, there's glucose. There's bonds of glucose. And what happens is, what we could do is we could take those bonds of glucose and convert it into a different form. And what actually happens when we convert it into a different form is it looks like the gummy bear explodes, but what's actually happening is the chemical bond energy in the sugar in the gummy bear is converted into light energy. So you see lots of light being emitted, and it's getting really hot, so it's converted into heat energy. So a lot of times energy can be converted from one form to another. Make sure you click on the gummy bear demonstration to see that, because it's really a great way to represent energy converting from one form to another. Now, there are also reactions with energy. There are two major reactions with energy that you need to know about, and they're endothermic reactions and exothermic reactions, and we're going to talk about what they are. An endothermic reaction is when there's a reaction in which energy is being absorbed. Endo, it's taking energy in. When you're taking energy in and absorbing it, that's an endothermic reaction. Exothermic reaction is when your energy is exiting, it's leaving, it's being released. So an exothermic reaction is when energy is released. Endothermic is absorbing, exothermic is releasing. You need to know this. You also need to understand how to write a chemical reaction showing energy with energy terms. So for example, you see in the slide window, this reaction has energy on the left side of the equation. So its energy is in the reactants. Now you have to determine whether that's endothermic or exothermic. Well, energy is in the beginning, right? You have the energy, you're adding the energy to the reactants. And it's not there anymore. That's because it was absorbed. Anytime the energy is on the left side or the reactant side, it's an endothermic reaction. And one of the ways you can remember that is the name Len. If energy is on the left, L, left, it's endothermic. Len, endothermic. As opposed to Rex. If you have an exothermic reaction, as you can see there, the energy term is on the right because you produce the energy. Energy is released at the end. So Rex, if it's on the right side, it's exothermic. So if you remember Len and Rex, those two guys, Len and Rex, you know that endothermic, the energy term's on the left, and an exothermic, the energy term is on the right. And you need to understand the difference between endothermic and exothermic. You also have to understand the direction of heat flow. Heat always flows in one direction, and you need to know this. Heat always flows from an area of high temperature to an area of low temperature. So let's say you have two substances that you put next to each other. One is 100 degrees and one is 50 degrees. Well, the one that's 100 is going to get cooler, the one that's 50 is going to get warmer. But why? What's happening is you need to know that the energy is being converted, or it's going in the direction from the 100 degrees, it's leaving that and going to the substance that's 50 degrees. Heat always flows from an area of high temperature to an area of low temperature. And it's very important that you understand that. You also need to understand the law of conservation of energy. The law of conservation of energy says that energy cannot be created or destroyed. It could just be transferred from one form to another. So we talked about in the gummy bear demonstration, energy is not created or destroyed, it's just converted. But using heat flow, we can also talk about that. Here, if you have an ice pack, for example, this is an ice pack, and you can't tell, but it's really cold. If I take this ice pack and I put it on my arm, first of all, what you need to tell me is, what's the direction of heat flow? Is heat going from the ice pack to my arm, or is heat going from my arm to the ice pack? Well, remember, heat always goes from high temperature to low. So heat, the reason why my arm is getting cold is because heat is leaving my arm and entering the ice pack. That's why the ice pack eventually, after a while, gets warm, because the heat is entering it. Now, law of conservation of energy says energy can't be created or destroyed. It's not being created or destroyed, it's being converted from my arm to the ice pack. Now, how does that show law of conservation of energy? It's because the exact amount of heat that leaves my arm is the exact amount of heat that's entering the ice pack. No more, no less. So you need to understand how that applies. And with a hot pack, it's the same thing. If I put a hot pack on my hand, what's going to happen? The heat is going to go from the hot pack to my hand. And the same amount of heat that leaves the hot pack is the same amount of heat that enters my hand or wherever you put it. So you need to understand energy in that sense. The next thing is the most important thing I could tell you right now, and that's what temperature is. Temperature, you know, 37 degrees Celsius, whatever it is, you need to understand that temperature is a measure of the average kinetic energy. And I'm going to say it again. Temperature is a measure of the average kinetic energy. And I'm going to say it one more time because it's so important. Temperature is a measure of the average kinetic energy. They ask this every single region. So it's very simple. If you have a substance that has higher temperature than another substance, it therefore has a higher average kinetic energy. You see these four substances on the slide window. These four substances each have different temperatures. They also have different masses, right? But Which one has the highest temperature? It's always the one that has the which one has the highest kinetic energy, excuse me? It's always the one that has the highest temperature. So the one with 60 degrees Celsius has a higher temperature than any other substance. It doesn't matter how many grams it has. It doesn't matter where it is. If it has 60 degrees and that's the highest temperature, that means it's the highest kinetic energy. And knowing that will get you at least 1 point, probably 2 or 3 on the regions. Make sure you know temperature is average kinetic energy. The next thing we have to talk about is phases of matter: solids, liquids, and gases. Now, how do we designate solids, liquids, and gases? We designate them with a little S, L, or G. So if we want to talk about H2O as a solid, we put H2O with a little S, as you can see on the slide. If you want to talk about H2O as a liquid, you take H2O and you put an L, and that's liquid. If you want to talk about H2O as a gas, you put H2O with a G. Very important. A lot of students don't really know what the S, L, and G stand for. Now you do. It represents the phase that the substance is in. And you have to know general facts about these phases: solids, liquids, and gases. Well, let's first do solids. Solids, very important. Solids are hard. Solids have a definite shape. If you take a solid substance, okay, it doesn't matter what it is. If you take any solid substance here, let's say here, this plastic right here is a solid substance. No matter where I take this plastic, no matter where I put it, the shape is going to be exactly the same. So it has a definite shape. Also, no matter where I put this solid, the volume is definite. If I take this solid and I put it in a different container, this is not going to change its volume. It's very hard and rigid. Nothing's going to change the volume of this. Solids, you need to know, have definite shape and definite volume. And a couple of things you need to recognize with solids. Solids have regular geometric patterns. What does that mean? It just means their shape doesn't change. It's a regular pattern. It does not change. Okay? It's in a fixed position. The particles in a solid are in fixed positions. And you know that. And also solids, the particles are very close together. That's solids. If you understand all of that, you understand solids. Definite shape, definite volume, regular geometric pattern, in a fixed position, particles are close together. Those are the generalizations about solids. Liquids, well, in liquids, the particles are a little further apart. They're not as close together as they are in a solid. They're actually spread apart a little bit. Now, if you take this liquid, this is H2O liquid. If I take this liquid and put it in a different flask, and I pour it in here, well, notice what happened to the shape. Well, it had one shape in here, and a totally different shape in here. So liquids do not have definite shape. Liquids can change shape depending on where they are. They take the shape of the container they're in. Their volumes, however, stay the same. If I took this, and this was 50 milliliters, and I poured the whole thing in here, this would still be 50 milliliters. And if I poured this whole thing in here, it would still be 50 milliliters. The only thing that would change is the shape. The volume would not change. So liquids have definite volume, but no definite shape. And the particles in a liquid, as they're moving, flow past each other. As you can see the liquid here, the particles, you can't see it because they're so small, but the particles flow past each other in a liquid. And a gas, now, with a gas, everything's a little different. Gas, the particles are spread apart even more. They're really spread apart, much further than in a liquid or solid. They're all over the place in a gas particle. Gases have no definite shape and no definite volume. Well, the shape's easy. If I had a gas and I put it in a different container, gases take the shape of the container. There's gas in here, you just can't see it. If I put it in here, there's gas in here. You can't see it. But gases take the shape of the container they're in. Also, gases, and this may be hard to understand, but you have these two different flasks. If I took all the gas that was in here, and I poured it in here, and found the way to get it in here, and I closed it up, the volume of the gas would take up this whole entire container. And then if I poured it back in here, it would take the volume of this container. So gases take the shape and volume of the containers that they're placed in. So it's very important that you understand for gases, they have no definite shape, no definite volume, and the particles are very spread apart. Now, you also have to know how to do particle diagrams for solids, liquids, and gases. And it's very simple. All they represent, if you have atoms of a certain element and you want to do the solid, well, you know that the particles are close together, so it will look like it does in the slide screen. For liquids, what do we know? Well, the particles are a little further spread apart. So, as a liquid, they're further spread apart, so you see that. And as a gas, they're even further spread apart, and as you can see in the gas in the slide screen, the particles are even further spread apart. So when they're asking you to do particle diagrams for solids, liquids, or gases, solids are close together, liquids are a little further apart, gases are all over the place. And it's really simple, and it's an easy way to get the points. Okay. Next thing we have to talk about is changing from one phase to another. You can have a substance as a solid, but then you could turn to a liquid, and you could turn it to a gas. It could be totally different things. Those are called phase changes. And you have to know all the different types of phase changes. And they can go in either direction. You can go from solid to liquid to gas by heating them. Right? Let's think about it. If you have ice, which is a solid, how do you turn it to a liquid? Well, you have to melt it. You have to add heat. How do you turn liquid to a gas? You have to add heat. Liquid to a gas is adding heat. So solid to liquid to gas, wait a minute, you should be thinking added heat? Wait a minute, didn't the Regents tutor say that adding heat was endothermic? That's exactly what I said. So from solid to liquid to gas, you're dealing with endothermic phase changes. Gas to liquid to solid, well, you have to start cooling it. How do you take a liquid and turn it into a solid? You put it in the freezer. If you want to have water, liquid water, and turn it into ice, you put it in the freezer. That's cooling it. So that's releasing heat. Gas to liquid to solid is releasing heat. Light should go off, and you should say exothermic. Perfect. Good. Let's deal with the endothermic phase changes for now. First one, solid to liquid. The first phase change that's endothermic is solid to liquid, and you need to know that is called melting. Another term for that is fusion. Now, there's a different fusion that you're going to learn about later on dealing with nuclear chemistry, and you can click on the concept if you want, but it has nothing to do with this kind of fusion. In this case, with phases, fusion is melting, going from a solid to a liquid. The second kind of endothermic phase change, liquid to gas. Liquid to gas is boiling. When you go from liquid to gas, it's boiling, or vaporization, or evaporation. Any of those three terms represents liquid to gas. And again, you have to add heat, so it's endothermic phase change. Liquid to gas is boiling, evaporation, or vaporization. And then there's one more that you may not realize. Normally when you heat something, you start with a solid, it goes to the liquid, and then after time it goes to the gas. But sometimes the particles in a solid are held together so weakly, they're still held together tight, but it's very weak, that as soon as you break the particles, instead of going to a liquid, it goes straight to the gaseous phase. So that's going from solid to gas, and that's called sublimation. And you have to understand with sublimation, you're going from solid to gas, but the reason that happens is because the forces or the attractions between the particles are very weak, which causes it to go from solid to gas, which is sublimation. So those are the endothermic phase changes. Solid to liquid, liquid to gas, solid to gas. And you need to know all of them. The exothermic phase changes are when you go from gas to liquid or liquid to solid, or even from gas to solid in rare cases. Let's take the first one, gas to liquid. When you go from a gas to liquid, that's called condensation. And again, you're releasing heat, so it's getting cooler, so it's exothermic. Gas to liquid represents condensation. How about liquid to solid? Liquid to solid is also releasing heat, but that represents freezing. Liquid to solid is freezing, or solidification, or crystallization. Liquid to solid, freezing, solidification, or crystallization. And then the last one is the weird one that doesn't really happen that often, is when it goes right from gas to solid, and that's called deposition. Gas to solid is called deposition. So to summarize the exothermic phase changes, it's going in the direction gas to liquid to solid. And if they ever ask you which of the following is an endothermic phase change, Well, they're going to give you 3 exothermic phase changes and 1 endothermic. So if they give you all one direction, gas to liquid, liquid to solid, gas to solid, and then 1 from the other direction, solid to liquid, you know you're dealing with the solid to liquid, the endothermic. That's just the rule if you really forget what you're doing. But you're not going to forget because you understand endothermic and exothermic. So you're not going to forget. You're going to understand what endothermic phase changes are or exothermic. I was just saying if one answer is the exact opposite of the other 3, that's usually right if you're really not sure. Okay, and the last thing we want to go over is the heating curve. The heating curve, as you can see over here, shows how the substances go from solid to liquid to gas. And in this case, you're dealing with water below its freezing point to above its boiling point. And the first thing here you have to see is that right here, well, let's go over each part actually. First, you need to know AB. You need to know what happens at every segment. Well, let's start with AB. Well, that's the first part, the coldest temperature. As you can see the temperatures here, the coldest temperature, you know that that's a solid. A solid, from line segment AB, you're dealing with a solid only. And what's happening over time? You're adding heat, consistently adding heat. So what's happening? The temperature's going up. So if the temperature's going up, what's happened to the average kinetic energy? The kinetic energy is going up as well. So in segment AB, you have a solid only, you're heating a solid, and you have an increase in the kinetic energy. You need to know that. BC represents, wait a minute, you have solid, but something's happening where the temperature's not going up. You're still adding heat, but the temperature's not going up. What's happening to the average kinetic energy? The temperature remains the same, kinetic energy remains the same. This represents a phase change. Anytime where you don't have temperature increasing, you're dealing with a phase change. This is the phase change between solid and liquid. So you have the solid-liquid phase change over here, BC. And what's happened to the kinetic energy? Remaining the same, because temperatures remain the same. But the potential energy, since you're adding heat, the potential energy is increasing. And that's what's happening at BC. The potential energy is increasing, kinetic energy is remaining the same, and you're going from solid to liquid. How about CD? At this point C, it's now completely a liquid. And for the whole line segment CD, you have just a liquid. Now, you're heating the liquid, the kinetic energy is going up, because the temperature is going up, and it's a liquid only. And that's what you need to know at segment CD. How about DE? Well, you know at this point, it was a liquid, now it's phase change because it's not changing temperature, so it's going from liquid to gas. That represents the boiling phase change. Liquid to gas. Now, what's happened to kinetic energy? Staying the same because temperature's staying the same. Since you're adding heat, the potential energy is increasing, so that's what's happening at DE. And again, you're doing a phase change, so the particles are starting to spread out to go from liquid to gas, and then at point E, it's now fully a gas. And what's happening in EF? Well, it's the same thing that happened at AB and CD. The temperature is going up, therefore the kinetic energy is going up. So at EF, you have an increase in kinetic energy, a gas only, and you're heating a gas. Now, if it was a cooling curve, which would be the opposite, starting as a gas, going down to a solid, everything would be the same except it would be reversed. So the kinetic energy would be going down, still remaining the same here, but the potential energy would be going down here. Decreased kinetic energy, decreased potential, and decreased kinetic. One thing to note also, here represents at 0 degrees, that is the freezing point or the melting point. Because in this direction, you're going from solid to liquid. But in this direction, you're going from liquid to solid. Solid to liquid is melting. Liquid to solid is freezing. And the point where it happens is 0. So that's the melting point and the freezing point. Here, you have liquid and gas, or gas to liquid, which represents the boiling point or the condensing point. And the boiling point here is 100 degrees Celsius. Now, the last thing we have to talk about are different terms: specific heat, heat of vaporization, and heat of fusion. The heat of fusion represents the amount of heat required to take 1 gram of a substance and melt it to go from solid to liquid. Heat of vaporization is the amount of heat required to take 1 gram of a substance and go from liquid to gas. Heat of vaporization. Vaporization is liquid to gas. Heat of fusion is solid to liquid, melting. So you know that's heat of fusion and heat of vaporization. And specific heat is dealing specifically with changing temperature. It's the amount of heat required to change 1 gram of a substance, and change it 1 degree Celsius. That's what the specific heat is. And there are math problems involved with that. But the math problems we're going to have you do as a separate concept, and you're going to do that separately. But you need to understand the heating curve first. And then once you understand the heating curve, then we're going to come back and you're going to go over the math problems relating to the heating curve and what specific heat, heat of fusion, and heat of vaporization represent. So I hope you learned a lot about matter and energy. We went over a lot of stuff. And matter and energy is actually really important. So it's really important that you understand everything about matter and energy. Now, after you go over the lesson, I want you to go back and I want you to go over every question on matter and energy. I want you to go over it and I want you to listen to the video explanation of every question on matter and energy, because that's when you're going to learn the most. When you hear the answers explained, whether you get them right or wrong, I want you going over them. And if you're still confused, come to the chats, look over your Regents Tutor review sheet, and go over the lessons again. And make sure, though, after you do this lesson, you also go over the heating curve math problems concept. Make sure you do that. I hope you learned a lot about matter and energy. I think you did.